All right, so next thing we're gonna do is we're gonna mill the top of this so that we end up with a flat surface on the top here, because this is all messed up from our cutting it, right? That's parallel with this surface, okay? So what we're gonna do is we're gonna mount it in the vise, and we're gonna use a face mill, which is gonna cut as it goes across the top, give us a nice surface. So before we can do that though, I have to make sure this vise is lined up correctly, because I had this vise, I was doing something else over here, so I moved the vise out of the way. So the vise is loose right now, okay? So the problem is, if I just slap this on here and tighten it down, this moves in this direction. It's called the x-axis, and this is moving in a very straight line, and it's perfectly parallel to this plane on the front of the mill here, and it's 90 degrees to the y-axis, which is moving this knob right here back in and back out, right? Well, what happens is, say I wanted to drill a hole on this end and a hole on this end, okay, and I wanted them to be exactly in the middle of the distance between this front face and this back face. Well, if the vise isn't set up so that these jaws of the vise right here are perfectly parallel with the x-axis, what will happen is I could set up the spindle so that I'm right over the middle of this, drill a hole here, but then when I move the table over, because this is turned, what's going to happen when I get down here? It's not going to be in the middle anymore, right? In other words, if I exaggerate it and I do it like this, you can actually see that as this moves, it's going to move off to the back, right? So before we do anything, we're going to make sure this vise is lined up correctly. That process is called tramming in the vise. I don't know why they call it tramming in, but that's what it's been called for like ever. So what we're going to do is we're going to make sure that this face of this jaw is going to be parallel to the x-axis, which will also be 90 degrees, which is perpendicular to the y-axis. All right. So what we do is we mount an indicator here in the spindle, or we mount an indicator in some way, so that we can actually have the indicator, the little finger on the indicator, measure here, and then we move it along the jaw, and that number shouldn't change, because essentially what we're measuring is we're measuring how much this jaw is pushing on the indicator point, right? Well, if this is perfectly parallel to the x-axis, as we move along the x-axis, the number shouldn't change. If this is kicked out too much this way, say this side is pushing on the indicator more than down here, we're going to see that the indicator number is going to change as the indicator is, as the vise is moved along the indicator point. Same thing if it's kicked too much that way. So we're trying to get it really, really accurate. But to start, to give us a good starting point, we can do a quick procedure to get it like kind of close, so that we don't have to be a mile off when we go to put the indicator in. So the easy way to do that is this side face on this vise right here. This is precision made to be perpendicular to this. So what I can do is, if I take a square and I put a square on here, I should be able to get pretty close to perpendicular, and then I'll be able to dial it in with the indicator perfect. All right, so anyways, so this is a precision square. Doesn't look precise, but it is compared to other squares. So what I want to do is I want to take this, and this has got a nice thick edge, and I can actually lay it right in this groove, okay, like this. because this groove is relatively parallel to the x-axis. So if I hold this in here like this, now this is relatively perpendicular to the x-axis. So if I can get this up against this or this, that would be great. The problem is, you see the base of the vise kind of sticks out and it's in the way. So what I'm going to do is I'm going to use a precision machine block. Okay, this is called the 1, 2, 3 block. The reason why it's called the 1, 2, 3 block is because it's 1 inch thick by 2 inches wide by 3 inches long. And they have all different variations of these with all different kinds of holes. This one happens to have drilled and tapped holes, large holes on the side, and there's all different kinds. I have a whole bunch of different ones of these. Okay, but this was made on a milling machine to very close to within those dimensions, and then it was placed on a surface grinder and it was precision ground to very, very close to these dimensions. Okay, so and whenever I say this is relatively perpendicular, relatively parallel, you know, that's because in machining you have what they call tolerance. In really old machines and stuff like this, you have a lot more wear and things that you have to factor in. Old tools like these and that have been around for a while, you know, you take a precision square like this and, you know, it gets bumped around and not taken care of, and sometimes it's just not as precise as they used to be. So what I'm going to do is I'm going to take this block, I'm going to hold this block in here like this, okay, and I'm going to bring this square right up against it, and I'm actually looking down at the gap between the two. Notice how the square up here where my finger is right here at this corner, see how the square is touching that? Mm-hmm. But do you see there's a gap at the bottom? Mm-hmm. All right.
Over that way.
So we're going to move this vise over, right? Oops, way too far. Okay. Oh, it's actually better. Now there's a gap at the top. So go ahead, just bump it over with your hand. Oop, let's see. Well, that's not too bad right there, right? Mm-hmm. The other thing you can do when you're doing something like this is you can put a light behind it and see if the light shines through. We're not going to get that crazy about it just yet. So what I'm going to do is I'm going to lightly snug up these nuts that actually clamp this down to the table. The reason why I'm not going to tighten it all the way down just yet is because we're going to put an indicator on there and we're going to see if we can't fine tune this a little bit.
Indicator, I think.
Yeah.
There.
We had indicators all over the place. Yeah, we can't use that indicator for this job though. That's called a drop indicator. Alright, so what I did was I put the mag base right on the side of the head here, because all I need is a good fixed point that's not going to wiggle around or move, right? Mm-hmm. And then we're going to put the indicator, the little finger on that indicator, see? We need that to actually touch on the inside here. So you do is you loosen this up. When you loosen this up, this is called a Noga indicator base. See, this one knob makes all of these joints, this ball joint, this flex joint, and the ball joint there, all loosen up. Huh? So what we're going to do, we want this high enough so that it's touching the part of the vise jaw above where those screws are. So we're going to get it so it's pretty close, so it's just like touching. This is a fine adjustment because this is so sensitive. Mm-hmm. See how it moves in and out? Yeah. So we're going to move it in so that we get the thing to just start to touch it like right there. Okay? And then we carefully turn this dial. We don't have to zero it, but... Alright, so see how it says 0? So we're set now. We're going to run that table down the other end and we're going to look to see exactly how much it moved. Alright, stop. Notice that the dial indicator is moving in that direction. The needle's moving that way, counterclockwise. Yeah. So that means that as we move down, this is pushing back, all right, more. So right now, those jaws are they're this way too much. So we need this end to go back while this end stays where it is, ideally.
You have rubber mallet.
So if I hit this on this corner, try and get that to come back near the 0. All right, Eden, so we fudged with it quite a bit now, and we're pretty close. There you go. All right, stop. All right, go ahead, run it back the other way. All right, stop. So from end to end, we're lucky if we're getting one full division on that indicator. But that indicator is a half thousandths indicator. So that means each one of these lines represents half of 1/1000th of an inch.
Yeah.
So that small amount of deflection over that distance is good enough
So that's all we
for our
have to do.
purposes. So no, now we're gonna tighten that down all the way.
Can you pull it towards you?
Yeah. There you go.
Wait, one more.
That's good. Okay. Now we're going to put an end mill in there. I'm sorry, a facing mill in there and get it all set up to cut. All right, Eden. Since we, I was going to use a, it's called a facing mill, but a facing mill can't take a very deep cut. And because this is so uneven, the way we cut this with the bandsaw and everything, I decided instead I'm going to try using what they call a shell mill, which can take a much deeper cut. See the shape of this right here? This is what's called an R8 taper. It's a special machine taper made. So it's very universal. So like this type of milling machine is commonly referred to as a Bridgeport. But this one's not made by Bridgeport, the company. Okay? This is made by Wells Index. But it's technically it's a knee mill. Okay, because this part right here that supports the table is called a knee. All right, it's a vertical milling machine. But Bridgeport was like the most popular one. That's why everybody in the machinery trade knows what a Bridgeport is. When you go into the machine shop at school, there's going to be a row of Bridgeports there. At least there's quite a few. Right. Not as many as when I was there, because when I was there, they were still using a lot of these manual machines. Now they use a lot of automated. Right, exactly. Okay. So, anyways, the point is, I can guarantee you that almost every single one of those machines there has an R8 taper.
Yeah.
Meaning the spindle right here is made to accept R8 stuff. So what's in here right now is what's called a collet.
Yeah.
This is an R8 collet. It's a spring collet.
I know
this
that
particular one's got the size on it of 1/2 inch. So that means you put a 1/2 inch diameter cutter in there or a drill bit, and when you tighten this down,
it clamps down.
It pulls this long bar that goes through the machine, pulls up on this,
and it clamps
down. See how that closes up?
Yeah.
All right. There's a little pin inside here. It's going to go in this groove. So I put this in, turn it until that pin lets this slide up. There we go, okay? When I hold it up with my fingers,
It pushes that
turn
out.
this rod until I know it's actually doing something, okay? Wrench. And we have to tighten this. This has a tendency, how that wants to turn. No, you don't want to do that, because then if it slips, this will slice.
And dice.
Right, so you actually don't even normally want to handle these without a glove on. Alright? What we have is we have a brake over here, okay? The brake is on right now, but it's not holding very well because I need to replace the friction pads in there. So what I do is adjust this fine adjustment so that now, let's see if that's locked enough.
When you move this, you can when you take it apart to move it.
I could fix that, yeah. The reason why I want that tight is because we're relying on the taper tightening to actually be what holds this from spinning. We don't want to rely on that little locating pin. We don't want to rely on that
It can snap.
because that can shear real easily, yeah. Tighten that down. Tighten it a little bit. Alright. Then you take the mallet, give it a light whack on the top there to seat it. A little better.
That good?
Again. All right. Now tighten it down all the way. Use both hands on there. There you go.
Good. Try it now.
Here, hold that. So we want this tight, right? Now we know that's tight in there. Okay. So we don't want this piece to go flying out on us, right?
That's why we wear safety glasses.
Yeah. So now, yeah, exactly.
This
Crank
one?
that. Yep. Crank that like that. That's going to bring the knee up. Which this is called the Z-axis, the up and down.
Yeah.
It's part of the. You remember something in your math class called the
Yes.
Cartesian coordinate system?
Yes.
X, Y, and Z planes? Right, all right. Stop. All right, now we're going to look at the way it's cutting here, right? This cutter is wide enough to take the full width if we position this correctly. So we're just sight down, eyeball at this now. Roughly the center line of this is roughly the center line of the cutter. All right. This is the lock for that. Front to back, because we're not going to move that. We do not lock this. This is the x-axis. We don't want to lock that because we're going to be moving. All right. Look at the way the teeth are.
Spin that way.
Has to spin this way,
Clockwise.
right. There's three things we got to take into account here when we're cutting. Speed, the RPMs that this is spinning. Feed, how fast we feed the work into the cutter.
Not fast.
And depth of cut, how deep this is cutting. So, I'm going to turn this on.
Switch doesn't work.
No, because I have this on a variable frequency drive, because this is a three-phase motor and I don't have three-phase power here. So that machine back there is converting it. The regular 220 volt power that's coming in from the
Holding
street.
some and
No, it's converting it into three-phase. It's not holding it. This is going to throw chips over there.
that's right.
Yeah, go ahead. Just throw it right on there.
On the right here.
On the piece. Yeah, that's good. There we go. That's pushing on the welder.
Can I open up this door?
Yeah. What I was gonna say was, actually, why don't we see if we can't I have that welder on casters. It'd be good if we could roll that welder out far enough so that we can finish this cut. That would be good. So my big giant air coat TIG welder is in the way, and what's happening is I run out of travel. And I usually compensate for that by putting the vise down one end or the other, respectively, and I totally forgot. Alright, and now that we got the damn thing sorted out, as far as the feed, we can feed it all the way down without it getting in the way.
3, 2, 1.
That looks okay. I'm satisfied with the quality of the finish that's on there right now.
Take the brush.
I don't think we need to change
Right
out to
there.
the fly, to not the fly cutter, to the face mill and do a final finish on that. We'll deburr these edges because they're razor sharp.
Do you have a grinder down here?
No, I actually use a deburring tool. It's just when you get the feet off, it just scrapes off the edge there. It's a soft aluminum, so it shouldn't be too hard. And then what we'll end up doing, we'll take this out. We'll transfer the position of the existing bolt holes to this piece, and we'll drill 2 holes, and then we'll mill pockets for where the part of the bracket's going to sit inside of it. We'll call that a wrap for now.